Last time we talked about SAM, social account matrix, and in this lecture we will talk about how to move from the SAM to the CG model. So let's remember the structure of our social accounting matrix as we elaborated last time through this Excel file. If you look at the activity factor, tax, and external accounts, you will easily remember what we did last time. Basically, we are here portraying the working of an economy, and each cell in the social accounting matrix you see in the SAM represent the behaviors, actually the transactions in the economy. But this is not really enough for us, as for reasons I will be explaining soon. But this is our starting point. If we don't have a SAM, we cannot have a C model most of the time. So recent CG models require maybe different data sets, but SAM is for 90% of the time, most CG models require a SAM. So remember this very well. And the first thing actually in economic analysis, whatever research you're into, is that know your data very well. Know your data, know how to elaborate on your data, and know how to work with your data. So this is the data we have in our hand, and usually we have numbers here. In this lecture, I'm going to talk about not computational part, which is the subject of next lecture. In this lecture, we will be talking about how to put these cells you see here as intermediate inputs, investment, governments, household spending, profits, wages, all these things, these cells we see here, how to put them into a machine readable form. But actually before that, how to put them in a mathematical functional form, and then next week we are going to put it in a machine readable form, I mean in a computational form. So these when I speak this way, these may sound a bit frightening because these are probably things you're not really familiar with, this kind of jargon. But you know, every discipline has their own language, and this is the language we use in programming. So basically what we're going to do here is let's see our SAM, and then I'm going to show you in the next slide the SAM we're going to use in the simple CG model we'll be working on, and later I will briefly discuss about the descriptively how to turn this SAM into a CG model, and finally we will be looking at the mathematical functions. And please don't get lost in the mathematics. I'm going to show you the formulas and the equations here, but I'm not asking you to master them very well, because what we're more interested here is basically how to put them in GAMS and then make our model, run it. If you're really interested in how to derive all these equations and how to but the textbook has a very good explanation in chapter 2, and if you're interested more about the maths behind it, you can find me anytime, and I can spare some time for you if you're interested, or actually I can also give you some extra materials if you want. But sometimes this is more than economic theory, it's more maths than economics. So basically CG is a mix of the two. So as I said, just know, because these are standard things, these are standard functions we use. So if you know the basic equations, and if you know how to put them in GAMS, and if you know how to put the code in the GAMS program, and if you master how the CG model works, you can actually try your own model by using the standard model. So basically I'm going to ask you to be able to build the SAM, then build the CG model, then work on your own model. So let's move on to next slide. See the numbers here, not words, and then we will move on to the part about how to move from SAM to CG. This is the first SAM we built last time. It's from your textbook, and I don't want to repeat the explanations here again because you have more than 2 hours of lecturing on the SAM in your previous lecture notes. Please follow them. If you find it difficult, then please refer to those week, second week, first week lecture notes, the PowerPoint files. So here is this very simple SAM with two activities, two sectors, which is bread and milk. For simplicity, we assume there are no intermediate inputs. There are no inputs used. Every production activity here is done by using capital and labor. So we have two factors, and there's only one household which is using this capital and labor to produce bread and milk, and these households are also spending all their income which they receive from the services of capital and labor they provide to production sector, bread and milk, and they use all this income and they spend it on, again, bread and milk. This is a very simple economy, and remember that there's no government, and so there's no external sector, which means there's no taxes. There are no taxes, there's no imports, there's no exports, and it's a very small, very simple, closed economy. This is a very nice way to start a CG model. Okay, step by step, we're going to improve on this, and then we will introduce the government and then the external sector. But let's first start with our small, I would call a village economy. So this is what we're going to do from now on. Okay, maybe at this stage you may be wondering, so if we have a detailed SAM which reports all the transactions in the economy, so why do we need a CGE if we know enough about the economy, just looking at the numbers? Why would we need a CG model? Is it not SAM not enough? Well, if you're interested in only a specific point in time, and if you want to just take a picture of the economy, which might be your objective, if you're just interested in that, well, SAM is enough if you're going to do a very simple analysis. But well, SAM is a very nice way to show how the economy is working, is organized. But remember, it is a very static equilibrium model. So there's equilibrium because rows and columns, the sums of rows and the sums of columns are equal to each other, which is perfect balance. So we call it equilibrium. You're talking about an economy in equilibrium, but there's nothing to say about prices there because you don't see them, and all you see is values. But a value, for example, if you do you remember the last SAM we had? For example, for bread, you saw bread. You saw numbers like 5, 10, 20, 15, things like that. So actually every cell you see in a SAM is a value, and value in economics comes from two things: price times quantity. So for example, if households are spending 15 yen on bread, for example, this 15 means price times quantity. What is the price of bread? Actually, we don't know. What is the quantity of bread? Again, we don't know. If the price of bread is 3, then you're actually consuming 5 loaves of bread, right? For milk, we see a number like 35, so we don't know the price, we don't know the quantity, but we know that total spending, total consumption is 15 for bread, 35 for milk. So even if there is a price, just assume that everything is worth 1 yen in this economy. If it's 1 yen, then bread is 1 yen and milk is 1 yen. So that means there's 15 loaves of bread and 35 bottles of milk. That is good enough, actually. For an economy, you just fix the prices here. Okay, well, if you want to know what happens when prices are changing, for example, if the price of bread changes from 1 to 1.2 or 1.5, then this number 15 you see here is going to change. It's going to change to 18 or 22 or something. So then apparently you will be having a problem that the row and column sums is not going to be equal. So well, you know the trick. You know how to make these row and column sums equal to each other. When one number changes, you want to just balance with looking at the same accounts row or column, and you can still work with numbers, play with numbers, and make a change. Actually, this is what happens when prices are changing in an economy. When price changes, basically a lot of things change. Well, income changes, and in this case, so many things will change. When the price of something changes, the value or the sales will change, and this sales will also be increasing the wages of the workers and things like that. You can actually see by working on this by yourself. So what you see in SM is fixed prices, basically. Even though you don't see the prices, they are there. You don't know them, but they are there, and they are fixed. They are not. There's nothing to do with prices, changing prices, because SAM is just for 1 year. Okay, and then we just call it static equilibrium. Basically, there's no substitution. Substitution means you don't know. For example, in this case, for bread and milk, we use capital and labor. Okay, but in what amount do we use capital and labor for production of, say, bread? So you can use bread. You can produce bread using different combinations of capital and labor. We don't know. Even if we know how much we pay for capital and labor, okay, you cannot say, for example, what if we decide to hire more labor and less capital? This is possible. I mean, for capital is the machines, right? And workers are what you pay to workers in the labor account. So, what if you want to hire more workers to produce more bread with a given amount of capital, which is machines? So, but here you do not say that. You do not see that because, once again, when you change these numbers, when I say hire more laborers, you're going to pay more to labor, so you're going to have a bigger number for wages. You see, so then you're going to change the whole equilibrium. So the model here, the SAM here is built so well, and it is so rigid that you don't want to change any of these numbers. So you don't want to change because you don't want to just destroy the perfect equilibrium. So that means there's no substitution. You cannot change prices, and basically, if there's no changes like this, you have no idea about how households are even behaving. So again, fixed prices, no substitution, and you don't get any much idea. You don't get really much opinion about the behavior of economic actors. So in this case, we have only household as the economic actor. So that's why SAMs are very, I would say, stupid models, and we need a more complicated, maybe, but a better model with more insights. That's why we need a CGE. So, but CGE allows for all these. You can get substitution. You can model the behavior of the actors. In this case, we will be modeling the behavior of households. You will see later, and we can also see what happens when prices do change, and with flexible prices, possibilities for substitution between capital and labor, and also we can model the behavior of the institutions, the households. But at the same time, we will be still using the SAM. I mean, all these numbers will be there. We will be all the model, the CGE model will be depending on these numbers you see in the SAM. So SAM has its constraints. Constraints are row sums are equal to column sums. All production is equal to total output, so all income is spent, so things like that. So we will still hold these constraints. We will not change them, but what we will do is to make all these cells, all these more flexible. So to put it in another way, we will say that SAM CGE does not ignore SAM, but it overcomes its shortcomings, and by overcoming we mean we need a functional form for each of the numbers in these cells, 5, 20, 10, 15. We will instead of working with these numbers, we will be working with functions. So functions means mathematical equations. So basically, as I said, each cell is actually represented by value, which is price times quantity. Okay, so each sum in the cell, now we can model with the CG model. We can just we will just be we will just see all these cells as price times quantity. Every cell is price times quantity. Prices are peculiar prices, quantities are peculiar quantities. Okay, so then our model will be able to determine prices and quantities. Okay, having said that, these are very abstract notions, I know. So and not even so sexy as they sound, because when you see the math, you will probably be a bit distracted. But please don't. As I said, I'm not going to ask you to. I'm not going to bother you to memorize, or I'm not going to bother you to at least elaborate on all in none of these maths. Just know the basics, just know where they come from, and spend more time understanding them rather than verifying them. But if you're interested, be my guest. So what we're going to do, we are going to model a very simple CG model. The CG model will have two sectors, bread and milk, two factors, capital and labor, one household, no government, no taxes, no external sector, no exports, no imports. This is a closed economy, just like something like North Korea. So Mr. Kim doesn't know that we're modeling his economy, but maybe he will be very interested if we show them this very simple CG model, which might work. Okay, so the next step is going to be casting this CG model into GAMS. I will not be showing them in this PowerPoint file, but on the lecture notes set 3, you have on a PDF file, you have the list of commands, the list of the programming code to put into GAMS. So please also do this, follow this simultaneously, and whatever you do here is going to have an application on GAMS. So I know it's boring at this stage, but once we're done with the model, you will find it more interesting. So for 2 weeks from now on, I guarantee you nothing but just boring details. But after that, I'm hoping to deliver much more fun lectures. Okay, let's move on to the next slide. Okay, here's what we're going to do. We're going to model each economic actor's behavior using our knowledge of economic theory. So that means we are teaching them, the economic actors, how to behave. And then we will calibrate our model, which means we will fit our equations to real world data, which come from the SAM. But this is basically a check that our equilibrium in the SAM, as shown in numbers, is actually verified by our equations in the CG model. So we call it calibration. Then we will define our restrictions or constraints, if we have any, for our model. We will actually discuss this later, so it may be a bit early for this, but this is necessary at this stage of modeling. Then finally we will define an objective variable. An objective variable is something that we want to maximize or minimize. In our case, we will maximize economic welfare, which is also named utility. And so we find the equilibrium, then we run our model, we find all the equilibrium figures. Okay, so this is what we're going to do, and in the upcoming slides we're going to discuss how these are actually done. So on page 14 of your textbook, you see the setup of the economy, which you can also see in the next slide. This is figure 2.1 from page 14. You can verify visually that it's a simple model with actually three kinds of behavioral equations. The first is related to households. The second set of equations are related to the firms and how they behave. So we will be modeling household behavior, firm behavior, and finally we will see how they get together in the market so that there's equilibrium. So we will be talking about market equilibrium. So before we start, I want to just read from your textbook the most important parts. Here it says that the household, we usually call it a representative household, consumes two kinds of goods. So these two kinds of goods are bread and milk, and these households are also owners of labor and capital. They use these and they use them in production. They provide them to firms, and then firms are paying them rent and wages for their capital and labor services. Okay, the firms produce either bread or milk. Okay, every firm produces only one commodity. So we have firms specialized in the production of bread or production of milk. Okay, so there's this clear-cut specialization. So we know now what the firms are doing, what the households are doing, and households and firms are both demanding and supplying these goods. Okay, so these two goods, and on the demand side, households are demanding the bread and milk, and on the supply side, firms are supplying bread and milk, and demand and supply will be equal to each other. So this equilibrium is the condition is very important. And on the factor side, this is the goods market. Okay, this is remember the circular flow diagram in the first lecture. This is the goods market equilibrium, and on the factor markets, there's a similar story. The factors, the use of factors, I mean the amount of capital and the amount of labor are in equilibrium, and there's a price adjustment here, flexible price adjustment. I mean the price of capital, price of labor are working to bring the factor markets to equilibrium. Okay, so this is a perfectly competitive market, which means there's no economic actor has any power in controlling the price, which means in economics we call them price takers. There's perfectly competitive market. So there are different kinds of markets like monopoly, oligopoly, these kind of markets. So we're not talking about such markets. This is a perfectly working market competitive market where the equilibrium price is settled by demand and supply, and well, this is basically the real world example of the market economy and the price mechanism. Here's a picture from your textbook, page 14, showing the structure of the model. It is a good idea to start from the bottom and read these, because this is the model. Well, in computer programming languages, they call this kind of things algorithm. What the CGE model does is something like that, and here is the algorithm. That's what we do. Okay, so from the bottom to the top, we can see and we can translate everything we see here into words. Let's see what is happening. At the bottom you see factors. These factors are capital and labor. This is for one sector. It says capital bread, the capital bread and labor bread. In one sector, on the bread sector, do you see at the bottom two factors, capital and labor, are used in the production process. So this production is Z. Z is the total bread produced. So ZBRD. So this Z is the total amount of output produced. Total amount of output produced in the bread sector. So the thing here is there is this word production. You see. So these two factors, capital and labor, are brought together to produce bread. Okay, the problem here is how is this production taking place, and how it is taking place. I mean, what amount of labor and what amount of capital used, and in what percentages, or in what combinations. So in economics, there are many ways to there are many ways that production factors can be organized to produce output. Each kind of organization is actually is some sort of technology, and we call all these combinations of capital and labor, bringing together to produce an output, we call it a production function. So basically these two boxes, capital and labor, are now aggregated into one Z on the upper level. So this production, as you see in this figure, actually means it's a production function. All these lines connecting boxes mean a function, and these functions can only be represented, can only be shown in the form of mathematical formulas. So that's what we're going to do. What you see in the SEM are only these boxes, okay, but not these lines. So the CGE model is producing you the lines, and these are the behaviors of the economic actors, of the market, of the households, everything you see here. Okay, so basically at the bottom level we see the firm behavior. They are putting capital and labor into production of bread. Remember, this is only for bread sector. There's also another sector, milk, and a similar story goes on also in the milk sector. So that's on the right part of the figure, but instead of drawing again, the author just preferred to put dashed lines. So the dashed line on the X milk is on the right side. It's actually a similar story. Production, consumption factor, the same sort of a picture is going to be also on the right side. They just made it short. Okay, so you can just duplicate it and put it on the right side, and you will have two sectors. Okay, let's just work on our bread sector. So at the lower stage we had a production function of the firms. Okay, so now we came up to the second step, which is Z. From Z, you see what is happening is now the firm produced bread. They are now bringing it to the market. Okay, the market. It is shipped to the market. So when it comes to the market, it is sold, and who's going to buy it? But now, okay, this is the market side of the story. So who's going to buy it? Households. These are produced to be sold to the households. Okay, now the households are buying them and consuming them, and because it's a very simple model, the households receive the income because they own capital and labor, and for this they get paid by firms. Okay, this income, they use all this income and spend it all on bread and milk. So here we're talking about bread sector. So the all output produced in the bread sector, Z, is sold and is consumed by households. okay, which is X. So I said all production is consumed. That means production is equal to consumption, which is Z is equal to X for bread. Okay, now we're at the upper level, the top level of the model structure. You see households, and so far we learned firms, how firms behave, how the market equilibrium is ensured, and finally now we have to say something about household behavior. So what do households do? Households are basically using their income. Remember, this is a very simple economy: no saving, no taxes, nothing. All income they get from capital and labor services, they spend on bread and milk. So they spend on bread and milk, which means there's a consumption of X, which consumption is X here. There's consumption of bread, consumption of milk. Okay, why do these? What do households get from the consumption? Basically, they get satisfaction, they get happiness. Okay, there are many ways to describe this kind of why we consume in our lives, but in economics we call it utility or welfare. So utility is shown as W here, UU. So this UU is utility, right? And what we do here is we want the household to be happy. So we want to maximize its utility. All the models, everything is here working for the household to get the highest possible utility, right? So this is our objective. And I think now the story is very clear. Firms are doing production using capital and labor. This capital and labor is coming from households. These households are working as workers, and they are working as also capital owners. They're giving capital to firms. They're giving labor to firms. They're labor services to firms, and then they get income. And they get this income. They spend on all the production of bread and milk. And then from this production, they get utility. They get welfare. So that's it. That's what we're going to. That's what we're going to model, and in the CGE, in the simple CGE model. Okay, from now on, from next slide on, we will look at each of these three things: firm, market behavior, market equilibrium, and household behavior, each one by one, and we will see how it is shown these functions. Remember, all these lines are functions, right? So at the production side, we have production function. Between Z and X, consumption part, there's also a function. Actually, this function is just an inequality. So which is total production equals total consumption. But inequality is also some sort of a function. And finally, we have at the top, we have households combining X of consumption of bread and consumption of milk to get utility. You see these two boxes, XBRD, XMLK. So bread and milk consumption are now providing the household utility through what we call a utility function. All these lines connecting boxes are functions. Don't forget that. And each of these functions means some sort of a mathematical equation. Okay, and these mathematical equations, it's not just maths. It is based on economic theory. So in macroeconomics courses you took, basically this is microeconomics. In microeconomics courses you took in your introduction to economics or intermediate economics courses, you didn't really deal with this kind of functions. But originally, what you know about utility, what you know about production, what you know about the market equilibrium, you just show them in the form of graphs, like demand graph, supply graph, such things you saw before in your education, in your economics classes. But that's one way, geometrically, one way to show demand, supply, market equilibrium, utility. But here what you're going to do is now put them in algebraic form, not geometric, but algebraic form. Okay, basically you will be doing the same thing. Maybe you will realize at the end, but just don't get again distracted, because geometry and algebra are the same things most of the time. Just visually, geometry, I mean, these graphs look much nicer, but algebra, well, it's the same language in a different form. So let's start with the household behavior in the next slide, which is page 15 and 16 in your textbook. Okay, on the demand side, now we need to specify two things. The income of households and then the spending of households. And finally, remember at the previous figure, we mentioned that households are spending on bread and milk to maximize their utility. So basically, we have a sort of a optimization problem here. So the behavior of an economic actor is usually formulated in the form of an optimization problem. Optimization problem is a maximization or minimization problem. So here we're talking about utility, and we don't want to minimize utility because utility means happiness. We want to maximize it. So we want to maximize the utility of this household. And when doing that, the household has some restrictions. Okay, so the household basically wants to consume more bread and more milk. But of course, to consume more and more milk, we need more income. So the amount of income, the amount of milk and bread you can spend depends on your income, right? So we here assume that your income is totally spent on bread and milk. So we assume here that total income of the household is equal to total spending, and then we have the utility function. Okay, let's now look at the two equations here, 2a and 2b, on the right side. So basically they say the same thing. The explanations are on the left. On the top you see the utility function. Here you see the multiplication sign, pi, big pi, and below that you see I. I is the goods. Okay, here we continue. We continue our notation using our notation I and J. Remember when we were putting them in GAMS, we used the command alias. Basically, I refers to the rows of the SAM, and J refers to the columns of the SAM. And you will remember that the columns and rows are actually the same accounts. So if you have two sectors I, J, this is basically bread and milk. So X is total consumption, and what you see here is another is an exponential function. Xi is the consumption of I, or spending on I, to the power alpha I. Here you see alpha. Alpha is a share parameter in the utility function. Basically, if you're spending 60% of your income on bread, then alpha is 0.6. And if you're spending 40% of that on milk, then it's alpha for milk is 0.4. So this is the multiplication sign. So the utility is defined as here. What you see here is an abbreviated form, but basically this means x bread to the power 6.4. Sorry, x to the power x bread to the power 0.6 times x milk to the power 0.4. I just assume that you're spending 60% on bread and 40% of your income on milk. So basically such kind of functions are called Cobb-Douglas functions, just because we have a name for this in economic theory. So this is a utility function in the form of a Cobb-Douglas function. We will soon have another one for production. We will also call it conduct this function. Any function which has the shape or the equation like as you see in equation 2.a, such functions are called Cobb-Douglas functions. The important characteristic of Cobb-Douglas functions are that the shared parameters alpha are defined for each product. So here I assumed for milk 0.4, for bread 0.6. If you add them up, you get 1, which is 100%. So if you add up all these alphas, you get 1. This is actually mentioned in the last line here. You see on the right, alpha is a number between 0 and 1. So we have 2 alpha because alpha comes with an index I, which is bread and milk. For bread, I just said it's 0.6. You can choose any number you want. And for milk, it's 0.4. Actually, I cannot assume like this. Okay, I'm just saying 0.6, 0.4. I'm just randomly making up numbers. But how do we know what alpha is? Okay, that's where you need the sum, because all these numbers, how much of your income you spend on milk, how much of your income you spend on bread, it is available in the sum. Okay, so right here we do not put numbers yet. All right, we do not put anything like 0.6, 0.4. I just want you to know that these add up to 1. These exponents here add up to 1. But what these numbers really are, we are going to get them from the sum. Okay, and then the sum, the GAMS, when we put this into the programming code, we will teach GAMS how to take these from the sum, calculate them, and then ask GAMS to because we will teach these equations on to GAMS as well. We will just put it in GAMS program, and then GAMS is going to calculate it for us, and finally solve all these equations. Okay, now we have talked about maximization of utility. Okay, then the second equation here is the optimization problems are written like this: maximize something subject to a constraint. Equation 2.b is the constraint, but we usually call it a budget constraint. Budget constraint is how you use your budget. It's about how you use your budget. So our constraint is such that you spend all your income on bread and milk here. So you see on the left side, you see a sign. These are Greek letters actually. This is the Greek letter sigma with an index, and at the bottom I. I is good, 2 goods, bread and milk. So that means you're adding. Sigma means adding. These are mathematical signs, and you probably remember these from your maths classes, calculus classes. So in equation 2.p, on the left hand side, you see pi multiplied by xi. Okay, so pi x here, as you see, x is not an exponent, it's pix. You see the glossary at the bottom of the equation. Pix here means demand price for good I, and then multiplied by xi, which is the consumption of the good I. So basically this works like this. This is the demand price. So what you see on the left side here, sigma pi times xi, is in open form. It would be something like this: demand price of bread times the consumption of bread quantity plus the demand price of milk times quantity of milk. Okay, this is it. But instead of writing it in a long form like this, the author and basically the GAMS modeler prefers to write it in equation on the left hand side of equation 2.b. Okay, this is what? This is your total spending. This is the price of bread times quantity of bread plus price of milk times quantity of milk. Okay, so what didn't exist in SAM is the prices. now we have them. So this is the left hand side. We know total spending. The right hand side is total income. Remember, the income of the household comes from capital and labor. So capital and labor are factors, and factors have their own prices. So the factors here are denoted as FF. FF here is so the index here is for H. H is the factor you're interested in, and for H, H can be either capital or labor. So PH with an F here, PH is the price of factor, and FFH, FF sub H is the amount of the factor. So basically the right hand side in open form looks like this: P capital times FF capital plus P labor times FF labor. In other words, it is price of capital times the quantity of capital plus price of labor times the quantity of labor. Okay, so this is total payments made to production factors, capital and labor. Remember, all these payments go to households. So now we know that this is total income of the households. And now we verify here in the equation 2.b that this is the budget constraint of the household. All income equals total spending. Okay, so if you look that, if you see them as mathematical mathematical notation here, you probably feel like an alien. But basically, the interpretation, as you see, is simple. Okay, so the whole thing here says that the host household is going to maximize utility 2.A, equation 2.A, subject to the budget constraint, equation 2.B. Right? So this is the optimization problem, and every optimization problem needs to be solved. But yeah, and every solution needs a method. Okay, so how do we solve this optimization problem? How do we get the solution, and what do we solve it for? Okay, so when you have a solution, you want to find a solution for certain variables. So what are these? We are looking for what are we going to solve these equations for? Okay, we're going to discuss that in the next slide. Maybe this is the tricky part, and if you're not familiar with optimization problems and how to solve optimization problems, I don't know whether they teach you in the Masters in Public Administration program. I believe you have I think you have a couple of classes about project management, and maybe you may have a class on linear programming or something like that. I'm sure that you have heard of this simplex problem if you've taken Umala Sensei's class. And so to solve for optimization problems, basically we use a couple of methods. In this case, we will use the Lagrangian multiplier. The whole process is written on the right hand side. I just copied and pasted from your textbook on page 16, I guess. Yes, it's on page 16. And what they do here is you want to solve. Okay, this is 2.C, 2.D, equations 2.C, 2.D. What you want to do is you want to solve all these for the amounts of spending on bread and milk, which is xi. You want to solve for xi, and also you want to solve for the what we call Lagrangian multipliers. So the Lagrangian multiplier is here denoted as this Greek letter. I think it's pronounced phi. basically when you solve all these what we call first order conditions, you get the optimal amounts of xi, which is the optimal amount of spending on bread and milk, plus when you solve for the Lagrange multiplier phi, you get the you basically get the demand function for good I, right? So this is in equation 2.1. So 2.1 is called a derived demand equation because we derived it using the Lagrange multiplier. So basically the implication of this equation is very easy in 2.1. It says the spending on good I, which is demand, actually demand for good I, it can be bread, it can be milk, is inversely related with PI, which is PIX, which is the demand price of the good, same good. So that means there's a negative relation between price and quantity, which is what you know as the demand function. It is the downward sloping demand function. You probably know about demand supply curves. Well, this is the demand curve for this product. It can be either bread or milk. Okay, so also don't forget that it is written in is written into equation 2.1. It also says that the demand for product I also increases with what you see in the sigma sign. Remember that sigma ph times ff. This is total income. So when total income increases for the household, they also increase the spending on good I, which is either bread or milk. So I think it's self-explanatory. There's nothing wrong as far as I see in the equations and in the optimal amount optimization problem results. So basically these are very easy to interpret. The only difficulty seems to be if you're not familiar with the optimization problem and how to solve it, and the Lagrange multiplier method, you probably need to work, and maybe you might want to refer to an optimization reference, some economics, mathematics for economics textbook. Probably Alpha Chang has written a very nice one. And Lagrange multiplier, you can get more about Lagrange multipliers here. Okay, in the CGE model, you don't need to do all these calculations. Basically, we don't put these. You will see later on that what we do is we teach the results to the CGE model. We're not going to write a Lagrange multiplier to GAMS, but we have to know the results of the Lagrange multiplier, which is equations 2.c, 2.d, and 2.1. We have to know the results of this optimization problem solution. So that's what we need. Okay, don't forget that sometimes we have to do some of these calculations by on the paper by hand. I mean the optimization problem here has to be solved. Okay, and you will just put the solution to the gaps. So I think that's so far so good for household. In the next slide, let's look at the behavior of firms. The behavior of firms is very similar to behavior of households. I'm going to be repeating the same story here. What the firms maximize is firms exist to make profits, so they want to maximize profits. Although we will have the perfect competition market here, perfect competition means profits are zero. So, but the maximization problem of the firm is basically they want to maximize profits, right? The market may bring those profits to zero, but the firm operates so that it wants to make the most of profit it can. So now we have to define the profit function. The profits here are shown as pi, the Greek letter pi, pi is similar to the Latin characters. The Latin alphabet is like P, so we use pi, the Greek letter pi, to denote profits here. So then, okay, remember the firm's behavior is just maximization of profits. So maximization of profits is very easy. I think you all have a very good understanding of the meaning of profit. Profits is total sales minus total costs. And in this very simple economy, total sales are very easy to calculate. Just multiply the supply price of each good, bread and milk. So in the case of, for example, the firm in bread industry, okay, multiply the price of bread with the quantity of bread produced, and from that deduct the total payments in bread industry paid to total payments made to capital and labor. Okay, the total cost of labor and capital deducted from total sales, you get profits in the bread sector. Okay, so this is what is the maximization problem for the behavior for the firm. The firm behaves such that it wants to maximize this difference between sales and costs. Okay, so we talked about the sales. Basically, sales are PZ. PZ is you see here on the maximization bar at the top. This PJZ. PZ is Z is for supply. So Z is ZJ. Okay, or ZJ is basically the output of the firm J. Okay, remember I and J are the same thing. J is the column and I is the row for the SAM. So basically this is total supply of the firm J. It can be firm bread firm or milk firm, multiplied by, but here you get the price. Okay, price times quantity. And this is important. Okay, then when you want to calculate profits, you have to subtract total costs. Total costs, just like what we did for households. For households, capital and labor are income, but for firm, they are costs because they have to pay for this in production process. So you get here in the sigma sign, which is the summation. Okay, the Greek letter sigma here, summation of PHF and FHJ. So PHF is basically the price of the factor H. So price of capital, price of labor, and FHJ is the total amount of factor H used by the firm. Okay, so if you're talking about, if J is bread in this case, what we do here is price of price of capital times the amount of capital plus price of labor times the amount of labor used in bread production. So that will give you the total cost of in the production of bread. Okay, so because we have a very simple economy, we do not pay anything other than these as costs. Okay, the production costs are only on the capital and labor. Okay, we will make it more realistic in the upcoming lectures, and we will put more like inputs and others. So we will maybe make it look much more complicated. But here, let's focus on this very simple example. Okay, this is the maximization problem. The firm wants to maximize these profits as defined here, and then and when there's a maximization problem, optimization problem, then there's a constraint. The constraint here is this is the constraint faced by firms in equation. This is equation, the second part of the lower part of equation 2.2 here. Z J is equal to Bj times the product here, the pi sign again, product of Fhj to the power beta H. Okay, now that's another ugly looking mathematical equation, but it's simple. This is the Cobb-Douglas production function. Okay, so the firm is facing a constraint here. Okay, what the constraint is, Z is production. Okay, production of J. Okay, J is either bread or milk. In the production process, the firm is doing this. It's using capital and labor, which is FH, right? F sub H. These are production factors. They're using product, they're using capital and using labor to produce the product J. Okay, and when they do this, there is here a shear coefficient. The shear coefficient is beta H. All right, beta H is again just like in the utility function of the household. Now this time it appears in the Cobb-Douglas production function of the firm. These are shares of factors in the production. So if, for example, if the cost of capital makes up 70% of the production, then you would say beta capital for J. Say if this is bread, if talking about sector J, beta capital is 0.7, and then the remaining part, beta labor, would be 0.3. Okay, so that means on the product part, this because this big pi, the Greek letter means product. Do this for each production factor. So that means if you're talking about bread sector, Z bread is going to be equal to B bread. We're going to talk about B in a minute. So Z bread is equal to B bread times amount of capital to the power 0.7 times amount of labor to the power 0.3. Okay, this is how it should look like in the bread sector if the relevant shear coefficients are 0.7 and 0.3 for capital and labor respectively. Okay, what is missing here is a beta. Is the beta figures. The beta figures, how do we get them? Again, we have the sum. We will calculate these from the sum. We have to look at the sum and calculate the shares of capital and labor in total cost of production. Okay, and then we will put them here in when we do it in GAMS, right? And then the GAMS is going to solve us provide us the solution. Now, the last thing to talk about here is B sub j. B is the scale coefficient. Okay, so here is the very interesting part about production function. Okay, we call this a Cobb-Douglas production function. Again, we call it Cobb-Douglas because it's a specific function, because the exponents beta here is 0.7, 0.3. Again, they make up 1. Okay, the explanation here is, as you can see, beta h is a number between 0 and 1, and their sum is equal to 1. Such specific production functions are called Cobb-Douglas production functions. All right, and then what you see as bj is a scale coefficient. Okay, b, if it is 1, that means well, there's nothing, so it is not it doesn't change anything. Okay, so if b is a number greater than 1, that means if we increase production factors, basically if we increase b, for example, here, if it is a number larger than 1, let's say 1.2, that means when you put labor and capital into a production process, you get more output. So when b changes, so if you put if you're using the same amount of capital and same amount of labor, but you're getting more output, that means their productivity is increasing. So we call it some sort of a efficiency parameter. So if, for example, in your company you introduce new kinds of management techniques like Kaizen or total quality management or things like that, so using the same amount of capital, same amount of labor, but you get more output, you can say that total productivity is increasing or total factor productivity is increasing. This is synonymous to saying that there's a technological change or there's a technical change in your company, which is a favorable one. You might want to say that, well, then this is a scale factor which is giving you an advantage in production. So if if the BJ, the scale and coefficient is high, that means productivity of the factors is high. Okay, so now this is a very beautiful part of the this is a very beautiful part of the modeling, CG modeling practice, because well, this is an exogenous number. Okay, you can choose to change it and see. Well, you can change these numbers. You can and see what happens in the economy. For example, if you introduce a technological change in milk industry, for example, if you want to see what happens, just you might want to change this number B sub j by 20%, and this will increase the production in milk. And if you want to know what happens in the economy, well, you can just all you have to do is run the model, solve it, and you see what happens. So this is very brief. This is a very introductory level of simulation, though, but a good one, and a good one to start with, actually. So it's too early to talk about that, but I want you to have an understanding of the meaning of this B sub j, this scale coefficient. If you know about microeconomics, you will easily remember that basically when B increases, then the production function is actually shifting. This is how we show it in algebraic form. When a function function is shifting, it can be shifting it can be shifting upwards or downwards. So just like there's a technological progress, the opposite also even may be true. There may be a technological degradation or something. So then in that case, using same amount of capital and labor, you get less output, which is also possible. Not much observed in the real world maybe, but it is possible. It's a possibility. And remember, CGE is a mathematical model, and mathematics, everything is possible. So you might want to just modify these numbers and see what happens. It is just called simulation. Okay, so let's move on to how to solve the firm's behavior, so firm's optimization problem. So what does the firm do to how does the firm solve this optimization problem? But in real life, no firm actually they do not really solve problems. They just do their business. But in mathematical terms or in economic theory, what they do is basically they solve this optimization problem. Here in equation 2.2, they maximize their profits subject to the production function. Production function is basically the total amount of resources they have and how they can use it. All right. So, also we talked about technology too. Given technology and given amount of resources, they want to maximize their profits given the amount of resources. Okay, that's what the equation 2.2, the optimization problem, says. To maximize profits, now again they do the Lagrangian multiplier method, as you see in the bottom part of this textbook material to put on the right. So what's the result? That's in the next slide. So when you solve the optimization problem for the firm, basically you get knowledge about, you have a knowledge about, or you get information about how much capital and how much labor they employ in production. But these are actually meaning optimal amounts of labor and optimal amounts of capital. All right, so that means, well, if you're familiar with Lagrangian multiplier method again, you will say that you're taking derivative with respect to capital and with respect to labor, right? And then if you do that, you get the equation 2.3, and then you also solve for the Lagrangian multiplier here, which is omega j. This Greek letter, which looks like the Latin word character W, is actually it's called omega. Omega, you solve for omega 2, and then if you combine all these, then you get the equation 2.3. 2.3. Remember, for household, you found something like this. That was a demand function for goods. Here, when you solve for this in the Lagrangian multiplier for firms, you get the demand function for now the factors of production, and that's equation 2.3. Okay, so this is what you put in GAMS, not the equations on the about those. We just put equation 2.3. That's it. GAMS needs only this. Okay, and then what you see in equation 2.3 is again something similar to what you saw for households in previous slides. Let's interpret this. Look at the equation 2.3. The demand for factors, the demand for capital or demand for labor, is inversely proportional to its price. So if price of capital, which is PHF in the denominator, if the price of capital is increasing, then you want to use less of it, and if the price of labor is increasing, which is wages, you want to use less of it. Okay, fair enough. And beta here is remember, beta is the share of the production factor in production, and here, as you see, it is important in determining here how much capital and how much labor is used in optimal amounts. Okay, this demand for the production factors are shown in equation 2.3. You see that when the price of the supply price of the good J is increasing, if the price of if the price of bread increases, for example, then basically its production is going to increase. This is supply. When price increases, production increases. So basically, we're defining the supply curve. All right. So the price of supply price is PZJ, which you see in the middle on the right side. Okay, so that says a lot about the firm's behavior too. So maybe a crucial factor here is beta, but the parameter beta. Beta, remember, is the share of capital, share of labor in total cost of production. We randomly made up numbers like 0.7, 0.3. These may be taking different values. If it's 0.5, 0.5 or 0.2, 0.8, and numbers like that. Remember, this demand for these factors are going to be affected by these beta parameters. So basically, beta parameters are showing how sensitive these how sensitive demand for production factors are to prices, and also the prices of factors, and also the price of supply price of the goods. So when I say production is going to increase when the supply price increases, and when the capital when the price of capital increases, demand for capital decreases. By how much? It depends on the value of beta. So beta is basically some sort of an elasticity. If you remember the elasticity in microeconomic theory, it shows the degree of it is the degree of sensitivity of one variable to when there's a change in another variable. So this elasticity here shows itself in the form of a parameter beta. So when we solve these, basically we get optimal amounts of capital and labor, and we now solve the equations for firm. We now have an understanding of the behavior of the firm. I don't know if you're feeling like you're tortured. That's how I felt when I started studying CGE, because I was dreaming about all this in my dreams, and I saw all this in my dreams at night, and I sometimes was actually daydreaming about all this. So if you spend a lot of time, you basically can just rewrite this textbook yourself. Okay, it's not maybe something to be proud of. Okay, now let's move on to the last part. Luckily, the market equilibrium. Okay, remember the figure in slide number 7? We had 3 blocks, right? Firm behavior, household behavior, and market equilibrium. We did household behavior, we did firm behavior. Now we are at the market equilibrium block. Market equilibrium is probably the easiest part. Now we solved for the problem of the firm, we solved for the problem of the household, but we have to link them. Otherwise, there's no equilibrium, right? So we have market for goods, we have market for factors, we have now households spending their income on goods, we have firms using capital and labor producing. Okay, but how are we going to link these? We know consumers, we know households are consuming goods, we know firms are producing goods, but how are they matched? Okay, so this is happening in the market. Okay, the market is not only for the goods, there's also the market for factors, right? And now it's time to link these. Otherwise, the model will not be, there will be just two separate firm and household equations, but if we don't link them up, then we cannot solve the model. That's why we need market equilibrium conditions. And remember, in the optimization problems, when at the end we solve for demand for goods and we solve for demand for factors of production. Demand for goods in the household's problem, and demand for factors in the firm's problem. We just did it. So also in the household and firms, Lagrange multiplier results at the end when we found these equations. In the case of firms, that's equation 2.3. In the case of households, that's equation 2.1. Okay, when we solve for these in, for example, in equation 2.1, you can switch back later on in the. That's in your textbook. Please follow that in your textbook. It's in page 19, and also please check the previous pages. Okay, if you look at equation 2.1 for households, you will see that in that equation you see Px. Px is the demand price for the goods, milk and bread. If you look at the equation 2.3 for firms problem, the demand for factors, you will see there's also another Pz. Pz is the supply price. Okay, now we found there are two prices for goods, bread and milk. On the demand side, we have demand prices for bread and milk. On the supply side, we have supply prices of bread and milk. Okay, if these are different prices, then there's no equilibrium. If these are different prices, basically there's one price faced by households, there's another price set by the firms. Okay, we must make sure that the prices set by the firms are actually the prices faced by the households. All right, so this is one thing to do. Okay, and that's in equation 2.6. Okay, precisely we say that price of supply price of firms is equal to the demand price of the households. Okay, so this is one equation. I started from the last equation in the list to equation 2.6. This is one of the this is one condition. Now we linked we linked the optimization problems for firms and households. And we solved them actually. We solved the optimization problems of firms and households. Now we linked them using one of these conditions. Okay, this is one condition for prices. Another thing we want to make sure is that total output is total output produced, total amount of bread and milk produced is actually equal to total amount of bread and milk consumed as well. So total production is equal to total consumption. Well, we made this assumption at the beginning of our CGE model when we looked at the SAM. We said that all output produced is going to be consumed. That's what we said. So we want to also show that, and that's equation 2.4, which means for every sector xi is zi. X is total demand and Z is total, basically X is total spending, right? So Z is total demand, so total supply is X is total demand. For every sector, for bread, so total supply of bread is equal to total spending on bread, and total supply of milk, again, is equal to total spending of milk. That's the market equilibrium condition. Total output is equal to total spending. There's one last market which we have to also provide an equilibrium condition for. That is the demand and supply for factors of production, capital and labor. So what we do here is the total amount of factors for each factor, of course, total amount of capital used in the production of bread and milk is equal to the total availability of the factors. For example, if you look at H is the sub index for factors. It can be either capital or labor. So that means total capital available in this economy, which is FF capital, is equal to total amount of capital used in two sectors, which is FF capital is equal to or the total FF capital is total amount of total available capital in this economy is equal to total capital used in bread plus total capital used in milk. Well, it's simple. Similarly for labor, total available labor in this economy is equal to, or you can call it just labor endowment, total available labor in this economy is equal to labor used in bread plus labor used in capital. So this is the last market equilibrium condition. Total factor demand is equal to total factor supply. Total factor demand by firms is equal to total factor supply. And remember, total supply of factors are coming from who owns them, basically households, and total factor demand is by who demands factors? It's firms. So total endowment of each factor is equal to, or total supply, total endowment is equal to total demand, and that's the last equation, which basically completes our model. Maybe it was difficult to see them when you saw them first in mathematical form, notation only, but as you see, its interpretation is not so difficult. And in the next slide, you can see as a list of you can see the list of all these equations, and that's what you input actually in GAMS. There you go. This is the model and it's all equations. You see 1, 2, 3, 4, 5, 6, 7 equations here, And what we will do is we want to maximize the last one, utility, and all the remaining equations you see here are coming from actually these. The first one is coming from the household's demand, household's behavior. This is the solution of the household's optimization problem. And the second one is the production function of the firm, and um, the second one is the third one is the solution of the firm's optimization problem. Okay, the household's utility function is at the end, in the last line. Okay, the equations in the fourth, fifth, and sixth lines. Remember, these are the market equilibrium conditions. So this is a very simple economy, simple CGE model. All we have to do is to solve this equation system. This is an equation system. We call it a simultaneous equation system because we have to solve all these simultaneously. And there's a mathematical condition for well, actually there's a linear programming condition for this kind of equation systems, which means the total number of endogenous variables, or the variables which for which the model is going to solve the values, the total number of endogenous variables is supposed to be equal to the total number of equations. Okay, so here basically, okay, we can talk about this later if you have any questions. I don't want to bore you with the details, but I think the textbook makes a really very good point here, and you might want to check the section on page 2021, especially footnotes 6 and 7. There's something called Walras law. The Walras law it says that when there are, for example, 9 markets in an economy, and if 8 of them are in equilibrium, then the 9th one is going to be in equilibrium as well. Okay, so there are a couple of more complications here. I want to save them to the practical part when we put all these in GAMS. Okay, what we will write in GAMS programming is these equations as you see in this slide, right? And when we do this in GAMS, I will spend some time explaining the computational part and the number of equations and the number of variables. The equality between the number of equations and the number of variables is more of a practical and computational thing. So I will leave it there. But if you're interested, please take a look at page 2021 in your textbooks. So I'll finish this lecture here. Hope you enjoyed it, and in the next one we will spend the next lecture notes set. We're going to look at how to do this computationally, and we will have more GAMS applications here, and the relevant section in your textbook is chapter the next chapter, which is chapter 3. Okay, see you next time.